Now I introduce iterative linear quadratic regulator for nonlinear systems. As we know, if a nonlinear dynamic system has a locally linear dynamic, and the cost function is a specific quadratic form, the linear quadratic regulator can be used to find a sequence of controls to generate the optimal trajectory from initial state to terminal state. Here, for example, this is the basic linear dynamic equation, and the corresponding cost function is quadratic, is in this formulation. Here, this first is for loss for terminal. This term is cost from the state, and this term is cost by the control. However, if a non-dynamic system is a strong nonlinear dynamic, so we cannot use the regular linear quadratic regulator to solve this nonlinear dynamic system. So we need to introduce a new idea to solve the strong nonlinear dynamic system. The idea we introduced here is the iterative linear quadratic regulator. That means we are based on the linear quadratic regulator result and find the improvement or modification step by step to reach the real nonlinear dynamic. The trajectory generated by linear quadratic regulator is called nominal trajectory. Nominal trajectory, that means we based on this nominal trajectory and prove the control step by step. Let's say one point on this nominal trajectory, x and control u. They have a deviation and denoted by this delta x and delta u respectively. So we got we not directly, repeatedly solve the linear quadratic regulator on the nonlinear system. Instead, we run a modified system and include a modified linear dynamic. This deviation from the nominal state and the nominal control. And then this is the still linear dynamic. And the corresponding cost function is also related with respect to the variation of the control. From this modified linear dynamic and the cost function, we can get a Hamiltonian function. It's like a Lagrangian at the nominal point. So we got this one, and here this factor is a Lagrangian multiplier. So our goal is to find, based on the result generated by the linear quadratic regulator, we need to find the modification or improvement on the control. So once we get this modification, then we get the improved control and run modified linear quadratic regulator again and again until we reach the convergence result. To do so, to calculate this improvement or modification on the control, this delta U, and we need to calculate the derivative of H with respect to this delta, this modification, this changes, and we get this first order equation, and we solve this equation, we get this modification on the control. Then we summate this modification we got from here to the state equation. That means the linear, the modified linear dynamic combined with the co-state, this equation about the Lagrange multiplier. And then we get this update equation for the state and for the Lagrange multiplier. Since we have this extra term, we cannot express the optimal control law in the linear state feedback form. So we need to think about another way. Let's say we add one term here. If we compare this equation with this updated equation, we can find this S and this V. Use this V and this S, we can get this modification on the Lagrange multiplier. And finally, we got we substitute this to the substitute this one to the state and the co-state equation. Finally, we got this control modification on the previous modification, on the previous control. Here is the optimal control. It's the control we got from a previous iteration and plus the modification in this iteration. This coefficients is calculated from this knowing matrices. Yeah, from this equation, we can see in the backward path. Backward path, that means we need from the path generated by the last iteration, and we can modify the control, get a new control. And then we use this new control to generate a new nominal trajectory. And then we change this path, this forward path and the backward path, and until we get the convergent result. For more details, please check with this reference. Thank you. Bye.